in between. Okay, so Specialist Maths Exam 2020. Let's rip in. So open it up. It'll come in two booklets, obviously, your exam will. But I've just printed it as one for ease of consolidation of resources. So let's have a read. We have, let f of x be this function here. We have x squared take 1 on x plus 2, and g of x is x take 2. Show that f of x is g of x plus 3 on x plus 2. Okay, so if we have g of x plus 3 on x plus 2, well, that's going to be x take 2 plus 3 on top of x plus 2. All right, and in order to collect like terms, we need to make this have the same denominator as this one. So we're just going to multiply this term by x plus 2 on top of x plus 2, right? We're not changing its value. There's the x take 2, and then we have the plus 3 on x plus 2 here. So that's our first step. Now they have the same denominator, so we can collect them at the top. So this is difference of 2 squares, so it will simplify to x squared take 2 squared. Then we have plus 3 on top of x plus 2, which is take 4 plus 3. That's x squared take 1 on top of x plus 2, which is f of x. Okay, anytime there's a show that, don't skip any steps, really draw out the explanation. Okay. On the axes below, sketch and label graphs of each function, including any asymptotes. So for part 1, we need to sketch f of x, which is worth 3 marks. And then for part 2, we're going to sketch the modulus of g of x. Now we're given the graph of g of x. That's this one here. All right, so I'm just going to do a rough sketch. For you, if we're sketching f of x, it's, we can think of it as this function here, or we can think of it as this function here. Either way, there's an asymptote at x is minus 2. So that should be the first thing that we consider. An asymptote at x is minus 2. And the rest, let's bring it up. Desmos is easiest for me. So our function is x squared take 1 on top of x plus 2. Alright, so there's our asymptote. Okay, now the reason they've got us to show that this is true, okay, the reason they've got us to show this is true is because what we can see here is, does anyone remember what that's called?
I don't know, but it's like a...
Yeah, it's an oblique asymptote, okay? So here's what f of x can be written like this or like this, right? Okay, so I'm looking at the graph and I can observe the asymptote, and then we can see it here algebraically, right? As x approaches positive infinity, as it gets really large, we have 3 divided by infinity. This part approaches 0, and so we're left with the line x take 2. As it approaches negative infinity, we have the same effect. We're left with the line x take 2. So there's an oblique asymptote at x take 2. So we need to sketch that, which also corresponds with g of x, doesn't it? So we've got an asymptote here. And let's label that oblique asymptote. Alright, and then we're ready to sketch the other parts. So we'll get that minimum point. The y-intercept is minus half. The x-intercepts are minus 1 and positive 1. Okay, so x-intercepts here and here. Y-intercept minus half, then there's a local min here, so it's looking like this. Alright, so I'm just getting those points. Sorry, it's not moving further away, it's moving closer to the asymptote. And then the same with them. I'll just get that maximum point, which is minus 3.7, and it's minus 7, so it's like here, and the function is doing this thing. Alright, so without having seen the mark scheme for this exam, I would anticipate you get 1 mark for each asymptote, so that gives you 2 marks, and then the other mark for the shape of f of x. Alright. Alright, so there we have part 1, that's f of x. Now we're ready to graph the modulus of g of x. Now remember, modulus of g of x just means the graph of g of x, but it's positive. So it's, I'm going to do it in a different colour, blue. It's this function. Alright, so that part's positive, and then this part, we just flip over the x-axis, we reflect on the y-axis, it becomes this line here. Now, you can copy it from your calculator, but if we want to define it in terms of absolute values, right? So if we have the modulus of x take 2, that's going to equal x take 2 provided x take 2 is positive, which is x is larger than 2. And it's going to be minus x take 2 provided x take 2 is negative, which means x is less than 2. Okay, so the function is minus x plus 2, so it has a slope of minus 1 and a y-intercept of 2. So we can get those values using our algebraic understanding of absolute value, or you can just graph this function in your calculator. It's 1 mark, don't spend too long on it. We should really just be able to reflect it using our ruler. All right, consider each of the following equations. State whether solutions exist. Where solutions exist, state the number of solutions and find the values. So this is going to be I'll just use our calculator to begin with. So we have x squared take 1 on x plus 2, and the asymptote, hang on, have I sketched the wrong function there? No, that's correct. And x take 2. Now, is there going to be any solutions here? No solutions, because x take 2 is the asymptote. So for part C1, we're going to write no solutions. That's all we're required to do, state that there's no solutions. If you want, you can address because it's an oblique asymptote, so the f of x function will never reach the value. Okay, and then we have f of x equals the modulus of g of x. So again, you can sketch both in your calculator. Okay, and now we can see we have 2 solutions. All right, they're there and there. Where solutions exist, state the number of solutions and find the values. Okay, so for part 2, we'll say 2 solutions. And these occur at x is minus 1.581 minus 1.58, and x is, they're plus or minus. How good is that? So we have 2 solutions. Now, just here, technically, like we're not required to find coordinates, we're just required to find the value of the solution. And so what we're finding is we're finding when does f of x equal g, the modulus of g of x? That's like, what are the x values that make that true? Well, it's true for these 2 values of x. Excellent, that's a lovely question 1. Let's proceed. All right, we have a polynomial question. Consider the polynomial. We have x to the 3 plus a take 4x squared plus bx plus 5a. All right, I'll write it up here, x to the 3 a and b are constants. 1, 0 is 2 plus I, state another 0. All right, we're experts at these. So if 1 is 2 plus I, the other has to be 2 take I. All right, hence find a real quadratic factor. So we know the sum of the roots, when we add the 2 roots together, we will get 4. And the product of the roots is 2 take I times 2 plus I. I'm going to do it in a drawn out manner, but we should be getting pretty good at this. This becomes a take b times a plus b, difference of 2 squares. So it's 4 take I squared. Now we'll just make the argument. I is minus 1, square root of minus 1, so when we square it, the square root and the square will cancel, so we have 4 take minus 1, we have 5. Alright, So that means the quadratic factor is going to be x squared, take the sum, plus the product. The sum times x. So it's x squared, take 4x, plus 5. Alright, so 2 marks there. Alright, part 1. If the remainder is minus 40 when p of x is divided by x plus 1, show that 6a take b equals 35. So here we're using the remainder theorem, which says if we divide by x take k, then p of k equals r. So that's what we're using here. So we're dividing by x plus 1, so that means p of minus 1 equals minus 40. So we're just going to put p of minus 1 into this equation. Alright, so we'll have minus 1 to the power of 3 plus a take 4 times minus 1 squared, take b plus 5a equals, and we're told 40, minus 40. Alright, and all we're going to do is solve through. Get the numbers and the letters by themselves. So what are we going to do? Minus 1 plus a take 4, take b plus 5a. Alright, minus 1 and minus 4 collect to minus 5, and we'll plus 5 to both sides. We'll get minus 35 over here. And we have a plus 5a equals 6a, take away b. That's required. Okay, so there's the remainder theorem. This is a good question because it brings together, like you've got your quadratic factors, you've got the remainder theorem, and now we've got the factor theorem. We have one factor of p of x is x take 3. So the factor theorem says if x take k is a factor, then p of k is 0. So we know that p of 3 is going to equal 0. Alright, we'll evaluate this. That's 27 plus 9a, take away, that's going to be 9, 4 9s are 28. Sorry, 36 plus 36. No, that's 3b. It's 3b plus 5a. Alright, so what have we got? 9a plus 5a, that's going to be 14a. We've got plus 3b. 27 minus 36 is minus 9. And then move it to the other side and get 9. Yep. Okay. Hence find the values of a and b. So if you want, you can solve by elimination, you can solve by substitution. The fastest way is going to be your calculator. Now you definitely want to get the mark here because they've given you both simultaneous equations. So here's equation 1, here's equation 2. And I'm just going to type that straight into my calculator in the simultaneous equation. Anyone solved it before me? What did we get?
I think a is equal to minus 3 and b is equal to 17.
Nice. Excellent. Okay, last one. Write the polynomial as a product of a real linear factor and a real quadratic factor. Now, this, we're not using what we've just solved. We're using a couple of parts previously. We're told one of the factors, and we find the other factor. Okay? So we know it's a cubic polynomial. We know that this is one of the factors, and we know that this quadratic is a factor. This linear factor is not a part of this quadratic factor because we know the roots of this quadratic factor, 2 plus I and 2 take I. So the polynomial then, as a product of a linear and a quadratic, is x take 3, and then the quadratic, x squared take 4x plus 5. And so this could be one that we go through, like you can expand that and confirm that you're correct if you find you have time at the end of the exam. But it's only worth 1 mark, so a pretty easy, straightforward question. So we're combining their parts, A part 2 and B part 2. Very good. Okay, on to some complex numbers. So we have 1 take I to the power of n and 1 plus I root 3 to the power of n. Find z1 and z2 in polar form. Alright, so straight to your calculator, although some of these, like you'll just recognise straight off the bat, like the 1 take I, so if you just start to think about it, real part's 1, imaginary part's minus 1, so it's here, has an angle of minus pi on 4, magnitude of root 2, so z1 is root 2 cis of pi minus pi on 4 to the power of n, and z2, so the real part's 1 and the imaginary part's root 3. So that's pi on 3, isn't it? But let's just check. All right, don't guess. So to convert, we'll go 1 plus root 3 I, and then I'll go option complex. 2 cis of pi on 3. And that's to the power of n. So we have z1 and z2. Okay, if z1 equals z2, show that m equals 2n. Alright, so we're going to equate them first. So we have root 2, and we have cis of minus pi on 4.
Do we apply de Moivre's theorem in A because it says also theta form? Many powers?
Yeah, we probably should, because it's 3 marks, isn't it? I've sort of probably only addressed 2 there. So yeah, maybe let's do that here. So this would be 2 to the half m, cis of minus m pi over 4. Now I imagine if you hadn't done it here, you're necessarily doing it in the next part anyway. So you won't lose marks, and markers are generous. They're looking for evidence of having applied it. So, if we were to do it down here, it wouldn't be of any significance. But you're correct. We should probably try and locate it in the correct position if 2 cis of n pi over 3. Yeah, let's do that. All right, so then, now when we make the statement of equality, what we have 2 to the half n equals cis of minus n pi over 4 equals 2 to the n cis of n pi over 3. So if they're equal, like you can equate the angles, or you can equate the modulus. If equal, then they're equal in magnitude, which means 2 to the half n equals 2 to the n. We have half n equals n, and we have n equals 2n. It's only 1 mark, so. Okay, hence find the smallest positive integers m and n such that z1 equals z2. Okay, so we want them to be the same. So we've got m equals 2n. So what we'll do then is let's perform a substitution. All right, so where m is, I'm going to write 2n instead. I reckon that might be the best way to do it. So we're going to take this, and we don't need to consider the modulus because we've already established that the modulus has to be the same. We're finding the angle where this occurs. So what I'm going to do for this part, which is part 2, I'm going to equate these complex numbers. So we have cis of, now it's minus m pi on 4, but I have n is 2n. So it's minus 2n pi on 4, and that's going to equal cis of n pi upon 3. Okay, so from here you can do a trial and error process. Okay, we want positive integer value of n, and then we can find m by timesing it by 2. How else could we go about it? We can divide. Let's do it like this. Let's see how this goes. We divide both sides by cis of 2n pi on 4. All right. So let's write it like this. SACE of minus 2n pi on 4. So rather than trying a trial and error process, let's try and do it like this. Okay, so on this side, that's going to simplify to 1, right? And over here, we can apply the properties of complex numbers in polar form, where we have SACE of n theta on SACE of phi theta is SACE of n theta take phi theta. So this simplifies to SACE of n pi on 3 take away minus 2n pi on 4. Now, is everyone okay with that operation? Everyone remember sort of bringing all that together? Excellent. So now 1 is SACE of 2 pi, or SACE of, it could be SACE of 0, but it's not going to be SACE of 0 because we have positive integer values. All right, that's the restriction of n. So we'll have SACE of 2 pi, and over here we have SACE of, all right, now if we to collect these, I have n pi on 3 plus, and that becomes n pi on 2. All right, so collect them. This one we're multiplying by 2 on 2, this one by 3 on 3. So this becomes 2n pi on 6 plus 3n pi on 6. We have SACE of 5n pi on 6. Okay, so then we're going, well, when does 5n pi on 6 equal 2 pi? All right, multiply both sides by 6. And then divide both sides by 5 pi. Now that is not an integer value, is it? That's 12 on 5. All right, so what that tells us is that's the smallest real number for which it's true, but it's not an integer value. We need an integer value. So then the next one would be, what, 24 on 5, such that z1 equals z2. Any ideas? On 5, so that's what, 2.4, 4.8. So 2.4. The next revolution would be 4.8, 7.2, and then it would be 9.6, and then it would be 12. All right, so n is 12. Okay, so let me just explain my reasoning there. This is not an integer value. All right, so I'm going, well, what's the next integer values that's occurring as a multiple of this? Because it's, we're going to keep, like, n is, that's not, it's one value that satisfies it, but it's a sequence of values, right? Because if you think of the unit circle, it just goes around and around, it's periodic, right? So 2.4, the next value of n that satisfies it is 4.8, the next value of n that satisfies it, 7.2, 9.6, so they all satisfy it, but they're not integer values. So we have n is 12, and if n is 12, then n is 24. All right. So that would be quite tricky to find out by trial and error because you're plugging in two values. So this is probably the most effective way to go through and do it. So there are tricky 3 marks to get. I would anticipate lots of people sort of got to here, but missing the next sort of step. All right, continuing on. Vectors. So we have points A, B, and C forming a triangle. All right, find vector A, B. So the vector from A to B is going to be the coordinates of A, coordinates of B take the coordinates of A. So 5 take 1, 4 take 0, 0 take 4. Find AB cross AC. So that means we now need to find, so that's A part 1, and then we have A part 2. We need to find vector AC. So 7 take 1, minus 6 take 0, and then 10 take This is interesting, isn't it? So 444, 666. So then find AB cross AC. All right. Would you like to do it manually or in our calculator? I reckon in our calculator, because it's going to be lots of 24s going on there, adding and subtracting 24s. So there's two ways in your calculator. All right, so there's from the program that we installed, and there's also in run that. I think be familiar with both. So A cross B, I have 4, 4, minus 4, and AC 6, minus 6, and 6. 0, minus 48, minus 48. All right. Hence, find the exact area of triangle ABC. Well, the area of a triangle composed of vectors AB and AC is half the modulus of AB cross AC. Now, if you use the program mode on your calculator, it actually tells you the modulus. It's half the square root of 4608, which is 48 squared plus 48 squared. And area is in units squared. Alright, point M divides AB internally in the ratio 3 to 1. The point N divides AC internally in the ratio 2 to 1. So we have AM equals 3MB and AM equals 2NC. Find AM in terms of AB. Alright, so I'll just sketch up the triangle here and I'll draw the parts on it, and I'd encourage you to do the same in the book. So we have A, we have N, and we have N, and we have C and B. And we have AM in terms of AB, we have M divides it in the ratio 3 to 1. Okay, so this is 3 parts, this is 1 part, and AC in the ratio 2 to 1. That's 2 parts, that's 1 part. Okay, find AM in terms of AB. Now we're even told AM equals 3MB. Right? So that's the relationship there. Or we can think of it like AM is 3/4 of vector AB. So that's what we should draw out here. Alright, that's 3 parts, that's 1 part, together they're 4 parts. This vector is 3 parts of that 4-part vector. So that's 3/4 of vector. And we know vector AB, 4, 4, minus 4. So this takes us to 3, 3, minus 3. Okay, find the exact area of triangle AMN. Alright, so here, like you can go through and find vector AN. We're told the coordinates of N, we're told the coordinates of M. So you can do it the long way, but they're looking for a, we always want to do the most efficient and effective way of doing it, right? So, triangle AMN, right, is equal to half the modulus of AM. So I'm going to draw out the argument a little bit here. AM cross AN. And we know AM, we know that that is 3/4 of AB. And we know that AN is 2/3 of AC. Okay. Now we can pull both of these out the front of the modulus, right? So it's half times the modulus of 3 on 4 times the modulus of 2 on 3 times vector AB cross AC. Now we already know the modulus of vector AB cross AC, that's root 4608. And then here we just have, 6 on top of 8, 24, which is a quarter. Alright, now, and part 2. Part 3. Find the coordinates of P on vector AC such that the area of triangle AMP. Okay, so that's this one. AM, so P is going to be here somewhere. Alright, is 1/12 of the triangle ABC. Okay, so how should we do this? So I would anticipate we're going to try and use something similar. We don't know the coordinates of P, we'll call them X, Y, Z. Alright, but what we do have is vector AP is equal to some scalar multiple of vector AC, right? So we have vector, because it exists on the same line, so we'll have vector AP equals AC. K times AC. Now, the area of triangle AMP, so triangle AMP is half the modulus of AM cross AP.
Attention students, can Darcy Reed and Letty Walters-Harvey please come to the front office? Darcy Reed and Letty Walters-Harvey to the front office.
And we have vector AM is 3/4 of vector AB. And we have vector AP is K times vector AC. Alright, yeah, here's how we do it, this is nice. So then we can pull these scalars out front. We have half times 3 on 4 times K times AB cross AC. Now this equals 1 on 12 K AB cross AC. Alright, now we're told, so this is the area of triangle AMP. Now we want triangle AMP to be 1/12 of the area of triangle ABC, which we found before is half root 4608. Okay, so based on this, K has to equal half. K equals half. So therefore, vector AP is half of AC, which is half of, and we found vector AC, worked it out. Was it the 777 or 666 or something? Half of
6 minus 6, 6.
Thank you. So that's 3 minus 3, 3. So that's vector AP. Now we want the coordinates of P, right? So coordinates of P. So again, I'm doing this in a drawn out manner. We have X, Y, Z. Take the coordinates of A, gives us vector AP. And the coordinates of A are 1, 3, 4 equals 3 minus 3, 3. So X take 1 is 3. That gives us X is 4. Y equals minus 3, and Z take 4 equals 3, Z is 7. Nice. Alright, so they're quite a tricky 2 marks to get, aren't they? That's quite a lot of work there. So in an exam, there's easy marks to get, there's hard marks to get. There may be a simpler way to get these marks. It's not immediately apparent to me. But I think we're all okay with that kind of reasoning, pulling these numbers out the front, solving for K. K has to be half. Okay, we have 1 on 12, 1 on 12. K has to be half because we know that that's root 4608. Everyone okay with it? Russell. Jack looks okay for you as well?
Yep.
Alright. Excellent. On to induction, question 5. So, here we have, use induction to prove that 7 to the n plus 2 is divisible by 3. This looks like a nice one. Alright, so remember state, that's not how I think of it, state. So P of n is 7 to the n plus 2 is divisible by 3 for all consecutive integer values of n. So we've stated the proposition in terms of PNN. Test for the lowest case. Test for n is 1. Which is divisible by 3. Therefore, P of 1 is true. State test. Assume K and A are integers. Let's see that. This is quite an easy one to do, really. Alright, make sure we get the line question. Alright, yeah, everyone okay with the proof? Yeah, go for it. And does this part need any explanation? Like, the link they're trying to make, we know that that's divisible by 3, and we're trying to see a link between that proposition and this proposition, 7 to the n take 1, and we should just see the difference is 3. So if I take the proposition that's divisible by 3 and subtract 3, well, 3 is still a common factor. That's what it simplifies to, so 3 is still a factor. Alright, so that's part B. On to part C. Now, it's a bit tricky, requires a bit of insight. It tells you using parts A and B. Now, I suppose the way to look at it is we've got this 7 to the power of 2n. And the only way we're acquiring that is if we're multiplying 7 to the n by 7 to the n. So the hint there, that's the hint really. If we have 7 to the n plus 2, all right, we know 3 is a factor of this. We know 3 is a factor of this. Okay, so this has a factor of 3. This has a factor of 3. So if we pull 3 out in front of both of them, 3 times 3 is 9. My suspicion is all we're expected to show is that the product of this. I haven't even processed it yet. I'm assuming it works out. So that's going to be 7 to the 2n. We have to take 7 to the n plus 2 lots of 7 to the n. Take 2. So we have 7 to the 2n plus 7 to the n. Take 2. And if you want more, like to communicate it, we can say the first and second, they're not terms, the first and second brackets both have a factor of 3. It's only worth 1 mark. Something like that. Very good. Integration by parts. Integrate arctan x. There's a bit of a hint here. Integration by parts is uv dash equals uv taken from u dash v. And so we want u to be easy to differentiate and v to be easy to integrate. So we know, like let's have a look at our integration rules.
So v dash is 1?
Yes. Yeah, and the hint there is we've got, if you look at what it integrates to, x arctan x. Okay, so that's uv, right? Very good. Okay, so if we go u is, u dash is 1. Sorry, I'm mixing things up. V dash is 1. V is x. U is arctan of x. And the derivative of arctan of x. Now, you might not know what the derivative of arctan of x is, but we do know that we integrate to arctan of x. So that's what you're expected to know. All right, we do integrate to arctan of x. So that's in 7b. All right, and so if we integrate 1 on 1 plus x squared, it equals arctan of x. Therefore, the derivative of arctan of x is 1 on 1 plus x squared. So that's the relationship there. So let's smash all that together then, using integration by parts. So we'll have the integral of arctan x equals uv, so that's x arctan x, take away the integral of u dash v. Now for the second part, I reckon we're going to need to use integration by substitution. I can't see a better way, unless we have a formula for that. I don't reckon we do. So I'm looking at the bottom right and going 1 plus x squared, that can be u. Here's a du, so we have 1 on u with regards to, alright, so let's do that. So let's go let u equal 1 plus x squared. Therefore, du on dx equals 2x. Therefore, we'll just process this part separately. X on 1 plus x squared equals equals the integral of half 1 on u with regards to u, which is half ln modulus u. And then plus c. So that's quite a bit of work for 2 marks. I suppose they do give you a fair bit. So I'll just put on this one. Alright, so that's the integration by parts. What's it say to do next? Consider the graph of the square root of arctan of x below. Consider rotating the graph about the x-axis between 0 and 1. Show that the volume of this solid obtained is this function here. Oh, that's a generous mark, isn't it? So, volume is the integral from 0 to 1 of pi times the function squared, which is the, so we'll really draw it out, pi times the square root of arctan of x squared, which is pi times the integral from 0 to 1 of arctan of x with regard to x. Don't forget your dx's like I do. I've had videos get like flagged before because the bell plays and it's playing music.
Oh.
It's like copyright. It's heaps annoying. So then it like mutes the whole video. Someone says to me, I go, I can't hear anything. Okay, hence find the exact volume. Alright? So if we want the exact volume, we're evaluating this integral here, right? So we'll just go straight from what we've got to up here. Now hence, okay, using what you've done, we've already demonstrated what the integral of arctan of x is, and even if you haven't done it, you've still got the formula to use. Sorry, I shouldn't have that integral there. It's x arctan of x, take that part, isn't it? So, straight into the fundamental theorem of calculus. X arctan x, take half ln 1 plus x squared. 1 plus x squared from 0 to 1. Okay. So it's that. Take away, and we put 0 in. Yeah, I think it's all going to go 0, so it's 0 arctan of 0. That's going to be 0. Take half ln of 1, which is 0. So that part's going to 0. So we're left with now arctan of 1, so that's inverse tan of 1 in your calculator, pi on 4. So all it is saying, when's the tan value positive 1? Well, it's when the x and the y component are the same on the unit circle, right? Which gives us an angle of pi on 4. So there are other values, but we have a restricted domain between 0 and 1, right? So pi on 4, so hang on, there's pi up front here. That simplifies to pi on 4. That's just going to stay as half ln2. And so we have here pi squared on 4, take pi on 2 ln2. Now you can check that you're correct, type that in, see that they're the same value to 3 sig figs. Alright, we're motoring through. Question 7. Using the fact that sine to the 3x equals sine squared x sine x, show that we have an integral here. Alright, so this is an integration by substitution. So we have integral of sine to the 3x, sine squared of x sine x. Okay, so we're going to let u equal sine of x. No, cancel that. What we should do, sine squared of x first, is 1 take cos squared of x. Isn't it? Alright. And so the reason we're doing that, I'll sort of draw it out for you. cos x. Du on dx is derivative of cos x is negative sine x. Negative cos x. Take negative u 3 on 3 plus c, which is cos 3 plus c. Nice. Everyone okay with that integration by substitution? So yeah, so the reason we did this is because if we try to do substitution here, we have u is sine x, well du is going to be cos x, so we can't use integration by substitution. We need to make this term in terms of cos x. I've expanded it. Even then, I didn't need to expand it, because if that's u, like the one's just going to disappear. So that's not something we needed to do, but this is a perfectly suitable way of expressing it. Okay, on to B. Figure 5 shows the graph from 0 to pi on 2. Find f of pi on 2. So sine to the power of 3 of pi on 2. So what we do, sine of pi on 2, and then raise it to the power of 3. 1 to the power of 3 is 1. Okay, explain why the function has an inverse. Alright, so this pops up a fair bit, and they're just looking for a function f of x. The f of x is 1 to 1. Alright, so that means each x value has a unique y value, and each y value has a unique x value. The other way of saying like why a function won't, we can say it's many to 1, like it has many values that satisfy both. Alright. On figure 5, graph the inverse function using symmetry about the line y equals x. So that's just up to you guys. Now remember, x coordinates become y coordinates become x coordinates. So it looks like this. So we know this coordinate, right? We know that coordinate is x is pi on 2, y is 1. So that means the coordinate here becomes x is 1, y is pi on 2. Okay, so that's where it finishes, and then you can roughly get those other coordinates. Something like that, isn't it? Only one mark there. Okay. Use parts A and B to show the integral from 0 to 1 of f of minus 1. Okay, so 4 tricky marks here, I reckon. So firstly, if we think of what we have is we have y equals sine to the power of 3x. And so if we want to find the equation of the inverse function, we can use variable interchange, right? So we can set x equals sine to the power of 3y. We can cube root both sides. Cube root of x, sorry, equals, and then inverse both sides. I'm not sure if this is helpful though.
X shouldn't be raised to the power of 3. Yeah. The third line.
Cube root?
Yeah, you've raised x to the power of 3 inside the root.
Yeah, that's cube root.
Yeah, but you raised it. Never mind.
Alright, is that useful? Use parts A and B to show that the integral from 0 to 1 of the inverse function. I reckon, what's another way we can think about this? So we look at this graph, the integral from 0 to 1 of the inverse function. So they want this area here. That's the area they're looking for. So here's probably how we should think about it. Okay, I think this is how we think about it. This area here, right, this shaded region, is going to be the same as this region here. Yeah? And not that we're rotating the volume around, but that would be the integral from 0 to 1 of the function of y. It's still the same. We use part A, so we've got the integration of sine to the 3x. Okay, how about this? Here's a better way. All right, so we want to find this area here, right? We want to find that area there. So here's how we can do it. Think of it in terms of this, right? Think of this as a rectangle, and the area of this rectangle is pi on 2 times 1. So the area of this rectangle is pi on 2, and then the area of this component is going to be pi on 2, take away that component, which is just the area of the curve of sine. All right, so you can see some of them require a bit of wrestling, as it's quite tricky to see, but they give you the pi on 2 out the front as well, don't they? So how can we communicate that? So let's try. We've got the integral from 0 to 1 f of minus 1x. Now what this is, I'm just going to go straight away and say that this is equal to pi on 2 times 1, so the area of rectangle, take away, and I'll have the rectangle on the diagram, take away the integral from 0 to pi on 2 of sine to the power of 3x. Take away the area under f of x. Alright, so that might be the best way to communicate it, which gives us pi on 2 take away. And from 0 to pi on 2 of sine to the 3x, we know that that integrates to, we'll just copy what they've got, minus cos x plus a third cos to the 3x from 0 to pi on 2. Now we know when we put pi on 2 in, it's going to be 0, and when we put 0 in, it's going to be 1. It's going to be positive 1. So we have to take 1 and then plus a third. Tricky 4 marks. I'll just, and like, we've got the answer, right? We've shown that it's true. The only thing I would probably like to do better is figure out how can I communicate the truth of this proposition. So that might be something that I come back to at the end of the exam when I've got a bit of time. But for now, I've sort of grabbed enough marks there. Let's move on to booklet 2. Eek. All right, consider the planes defined by the equation below show that plane 1 and plane 2 intersect along this line, showing all row operations. Okay, so we have two planes X. Now I'm just going to go straight to row echelon form augmented matrix we call it. Row echelon form to reduce it. 1, 1, 2, 4. 2, minus 1, 1, 8. Okay, so that's our matrix, and our first step is to get a 0 here. So we're going to go replace row 2 with 2 lots of row 1, take row 2. Okay, that's going to give us row 1 stays the same. 2 take 2. We'll have 2 take away minus 1. 4 take away 1. 8 take away 8. So then we can solve through. We go let z equal t. Therefore, 3y plus 3t equals 0. We have y is minus t. And we'll have x take t plus 2t equals 0. X equals 4. Sorry, it is over there. Equals 4. So x equals 4. Plus t, 4 take t. Alright, show that A and B lie on the line. Now the fastest way to do this is going to identify the value of t. So for point A, the value of t is 4. We can see that by equating t with the z component. So we'll just say when t equals 4, line 1 is, and we should show the working, it's going to be 4 take 4 minus 4, excuse me, I should call it as equivalent, 4 take 4 minus 4 and 4, which is 0 minus 4, 4. And when t equals 3, line 1 is 4 take 3 minus 3 and 3, which is point B, which is 1 minus 3. Show that point C is on plane 2. So plane 2 has the equation 2x take y plus z equals 8. Here. Now, C is 422. We'll just show that C satisfies P2. Figure 6 shows plane 1 and plane 2 and the line L1 where P1 and P2 intersect. The normal to P2 through C meets P1 at D. Find the normal equation, find the equation of the normal to P2 through C. Okay, so the equation of the normal, so we're looking for the equation of the line still. Now, it's the normal to P2. So the normal to P2 has direction vector 2 minus 1, 1. Okay, that's its direction. Now we'll need a new parameter, so plus lambda, and we know that it passes through, excuse me, I've got that round the wrong way. It's lambda times the direction vector plus the coordinate. And the coordinate is C, and C is 422. Alright, just as find the equation of the normal, so that's perfectly adequate. So it passes through C with this direction vector. Alright, show that D has the coordinates 0, 4, 0. So D occurs when this line, I'm going to call it line 2. So D occurs when line 2 coincides with plane 1. So what we're going to do is substitute the equation of line 2 into plane 1. So plane 1 is x plus y plus 2z equals 4. So we'll have 4 plus 2 lambda. We'll have 2 take lambda. And plus 2 times 2 plus lambda. Solve through for lambda. So we got 4, 6, 10, 2, 1, 5. Now here's like, it's getting late in the exam. You know, you make a mistake here, it's going to be an error carried forward. So let's make sure we're doing it right. Okay, so I'm just going to check, do I have the equation in plane 1? Good, okay. And then we've got, this is the direction of plane 2, 2 minus 1, 1. And it passes through this point here. So then I'm going 4 plus 2 lambda, yep. And I have take away, okay, I missed that. Didn't I? No, no, that's correct. 2 take away lambda, yep. And then 2 times 2 plus lambda. So that gives us 2 lambda. This is 3 lambda. Is it 2 lambda, 1 lambda, 3 lambda? Yeah, much nicer, okay? Check. Better to go slow and check. Otherwise, if I just continued on, so this gives us 3 lambda is minus 6, lambda is minus 2. When lambda is minus 2, L2 equals 4, 2, 2. 2 1, which is D, which is 0, 4, 0. Okay. Then we have from A part 1, the parametric equations for L1 are listed here. Find the coordinates on L1 that are closest to D. Okay, so this is when is the line closest to a point, and it's when they're perpendicular to one another. We have a formula for that. So it's from chapter 6. Shortest distance from a line to a point. And that's when PR dot B equals 0. So we'll just sketch a diagram for you. It's when the dot product of their direction vectors is 0. Alright, so we've got the points, we've got coordinate D and the direction vector of the line. So the direction vector of the line, so let's say here's the line, and we're asking about line 1, and it has direction vector minus 1, minus 1, 1. Okay, and we're asking when is it closest to D, which is 0, 4, 0. Okay, very good. So, sorry, we have the parametric equation of this line. So, let's list the whole, rather than just the direction vector, because we want to know that vector in terms of the parametric equation. So we have 4 take t, we have minus t, and we have t. Okay, that's the equation of line 1. Now so this is point D, and let's call this point P. Alright, it's going to be some point on line 1, and this point is going to be closest to D when they're perpendicular. So we need to find out, we're asked to find the coordinates of point P. So it occurs when vector dp dot the direction vector of L1 equals 0. All right, so that's where this formula is coming from, right? It's when the dot product's perpendicular. When it's perpendicular, that's when they're closest together. Now, the vector from D to P, well, the coordinates of P are this. They're in terms of T, right? So the vector from D to P is going to be 4 take T take 0. It's going to be minus T take 4 and T take 0. So that's vector dP, and the direction vector of L1 is minus 1, 1. And we're just going to evaluate T for when this equals 0. So we're going to have minus 4 plus T, we'll have plus T plus 4, we'll have plus T equals 0. So minus 4 and 4, we have 3T. T is 0. And when T is 0, L1 is 4, 0, 0. All right. How much closer is D to plane 2 than it is to L1? Okay. So this is the coordinate of P. All right. So this is 4, 0, 0. Now, the distance from D to line 1 is just that modulus there, so we can evaluate that. So the modulus of dP, modulus of dP, now the vector from D to P is just going to be what, 4 minus 4, 0, and this has a modulus of root 32. Okay, so that's how far dP is, from D to P is, so that's the first part of it. And so then we go, well, what's the distance from D to plane 2? All right, and that's just the distance between D and C. Okay, good, we don't have to do a formula for, because, now we know that's true, we can see it from the diagram that D lies along that line, but we can also see, we described point D as the point that occurs when the normal from plane 2 through C touches plane 1. So we know that that's what the coordinates of D are. So vector DC, the modulus of vector DC is the modulus of, again it's going to be 4, 2, 2, which is what, square root of 16, 20, 24. So how much closer is D to plane 2 than it is to plane 1? So root 32 take root 24. That's how many units closer it is. All right, is that making sense? That's quite a tricky vector question. So if you think, like from the diagram there, you've got D to C, and then the distance from D to P. All right, and what we found out is this is root 32, and this is root 24. So how much closer is it? What's the difference between them? Or that the big one and the small one. That's how much closer it is. Very good. Nice. We get a parametric equation one now. So, would you like to, we've probably only got one question left in terms of time. We can do the parametric equation, or we can do the slope field question. Any preferences? Probably, I would expect you to be able to get most of question 10, okay? So I'll get you guys to have got question 10 by yourself. Let's do question 9. Let's try to finish it. All right, so consider the parametric curve described by this equation. Show that the points satisfy the Cartesian equation. All right, so all we're doing is some substitution. we have cos squared of t plus sine squared of t plus 2, take 2, squared equals, so this is like the left-hand side, equals cos squared of t plus sine squared of t, which equals 1, which is the right-hand side. Alright, on the axes in figure 8, draw the curve above. Alright, so straight to your calculator, we'll restrict the value of t from 0 to 2 pi. We have an x value and a y value, so parametric type, delete all others. Parametric, alright, cos t and sine t plus 2. And V window, change your V window to match it. So we go 0 to 2 pi for t, and we've got minus 3 to 3 on the x-axis and 0 to 4, sorry, minus 1 to 4 on the y-axis. And it's just the equation of a circle, isn't it? Oh, dude, we could have just done it from above. That's why they showed us the Cartesian form. So sometimes, like this late in the exam, you won't recognise those things straight away. You just, all right. So we have, so if I just write that out, x squared plus y take 2 squared equals 1. Right, that's the Cartesian form. Okay, so this is a circle. Its centre is x is 0, y is 2. So you learn that in year 11 methods, and it has a radius of 1. All right, so that's what it's looking like. Silly goose. All right, using part A, part 1, and implicit differentiation, show that dy on dx is this. All right, so we'll use the Cartesian form. So we're going to take this and we're going to differentiate it with regards to x. So I'm going d on dx of this whole equation. So the first term is going to become 2x. The second term will become 2, y take 2 to the power of 1. And then dy on dx. And on the right hand side we'll have 0. Now we're solving through for dy on dx. So this is 2y take 2. Dy on dx equals minus 2x. Minus 2x on top of 2, y take 2. Minus x on top of y take 2. Alright, so you see this as well, like, there are easy marks, like there are 2 really easy marks to get. Compare that with 2 tricky vector marks earlier on where we were finding the area of that triangle. So you've got to make sure you get these easy marks, okay? And on the curve you drew, mark the point A for when t is pi on 6. So you can trace on your calculator to do a g-solve when t is pi on 6. Or you can go, oh yeah, cos of pi on 6 is root 3 on 2, and then we have sine of pi on 6 is half, plus 2, 2.5. It's going to be about here. And mark it on the curve, mark the point A. So we should call that A. Find the equation in the exact form of the tangent. All right, am I going too quick or we're okay? All right, so tangent, we need 2 things. We need the point of contact and we need the slope. So the point of contact is the x value and the y value of A. And I said just before, the cos value of pi on 6 is root 3 on 2. The sine value is half, and so we have half plus root 3 on 2. So that's half plus 2, sorry, that's 2.5. And for the slope, well, this is the dy on dx equation. All right, and so the slope at that point is just the x value, the negative x value on top of, negative x value on top of the y value take 2, which is going to be half, AD on BC, where we have negative root 3. All right, now most of these numbers we should be starting to know pretty well. Yeah, so pi on, like root 3 for example is like 1.73. Okay, so we've got that, and you can check on your calculator by g-solving that point or seeing the slope for that value. Alright, so we have slope of minus root 3 passes through this point. So we have y equals minus root 3x plus c, and we have when x is root 3 on 2, y is 2.5. So we're adding 1.5 to both sides, c is 4. Therefore, alright, and maybe the best way to check would be to graph that line. So minus root 3x plus 4. Look at that gorgeous tangent there. Okay, beautiful. Alright, how are we going? Bit to do still, 6 minutes. Figure 9 shows a circle in the complex plane and the tangent to the circle from the origin, meeting the circle at point P in the first quadrant. Ooh, okay, write an equation Z that describes the complex numbers that are represented by the circle. Alright, how do we do this again? So, the complex numbers represented by the circle. So we have the modulus of Z take 2i equals 1. How does that sound? Alright, modulus of Z take 2i equals 1. So how did I get that? Alright, we're drawing the complex number from the initial point with the imaginary component of 2i, and the radius of the complex number circle is 1. Okay, find the complex number. So this here is, if you want to recap that, it does pop up a fair bit. It's late in the textbook chapter of complex numbers, and in fact we supplemented it in the notes book. What's it called? It's 4F. It's 4G.
Is this when we do like the substitute z for x plus y?
Yeah, that's right. Yeah. It's yeah, I'll need the complex numbers notes book to remember, but it's basically just drawing, talking about arguments and moduli in the eigenplane. Yeah, can't remember the exact name. All right, find the complex number represented by p in exact polar form. Okay, so p is located. What are we told about p? P is the tangent from 0, isn't it? It's tangent to the circle, so it meets at 90 degrees. All right. So what that means, if we think of p, all right, this has a length of 2. This angle is 90 degrees. Okay, and this length is 1. All right, so we can find, if we want to describe p in polar form, we want to know what's the modulus and what's this angle. Yeah? Okay, this angle here, and we'll find this angle by finding the interior angle and subtracting 90, and the modulus here we'll just use Pythag. Okay, so the modulus of p is the square root of square root of p squared plus 1 squared is 4. So p equals p squared is 3, p is the square root of 3. Alright, and as far as phi goes, tan the sine of O on H, so we have sine of phi is half, and half is pi on 6. This angle is pi on 6, so theta is pi on 3. Alright, everyone okay with that kind of reasoning?
Is the root 3 for p plus or minus, or is it just?
Nah, because it's modulus, it has to be positive. Yep. So that's it in exact polar form. Okay, explain why for all z on the circle, pi on 3 is less than z, which is less than 2 pi on 3. Explain why z for all values of z on the circle. Okay, so so point P occurs at pi on 3. So I'll tell you about it. This might be our last one, I suppose. I'll tell you. We can probably answer the next two parts. We might get there. So what's going on here? Here's our argument plane. Here's a circle, and this tangent here. Okay, the value of the angle that provides you with that coordinate is pi on 3. Okay. So that means an angle between pi on 3 and this value here, when it's the next tangent, which is 2 pi on 3, all right? All of the points around the outside of this circle are going to have an angle that lies between that region. So that's the answer to that, all right? Think of the best way to articulate that.
How do we know it's 2 pi on 3 though?
How do we know this is 2 pi on 3? So I think the same way that we know that this is pi on 3, all right, it's going to occur when this length is 2, this length is 1, so we know that that angle, we know that's 90 degrees. We know that's 90 degrees, we know that angle. Pi on 2 plus that angle gives you the 2 pi on 3. Okay, all right, quickly, find the exact coordinates of P. That's pretty easy. P occurs at the angle pi on 3. So you can just convert that to Cartesian form. All right, that's done. Transfer point A from figure 8 onto figure 10 below. All right, so here's P and here's A. Find the exact coordinates of the point X where the tangents intersect. Okay, so we want to know when do these two tangents intersect. All right, well, there's a long way to do it, which is to find the equation of the tangent. There's a geometric theorem we could use. Find the tangents. Yeah, I think probably the best way is finding the tangent at P and then solving it. Anyway, I'm cooked. How about you?
Yeah.
I've got a double maths lesson now as well. Hopefully they're not like no more exams.